The title of my talk is the study of high TC yttrium-bearing copper oxide doping with some strontium. This work is in collaboration with Houston Group and Lucky, Dr. Huang, and Los Alamos, and the Marshall Space Flight Center in Huntsville. Well, since the first discovery of the yttrium-bearing copper oxide with a transition temperature about 98 degrees, and we have done extensive work. And here, I want to show the result we obtained from the magnetization measurement. Here, I showed this is the measurement of the sample, which is 0 cool down to 5 degrees Kelvin. With the field then we turn on the field to 75 Gauss and keep that field for about 3 hours. Okay. Then at this same field, we raise the temperature to 20 degrees. Then in 5 minutes, and we can start to, we monitor the magnetization. You can see this time-dependent behavior of this magnetization. And we fit the curve by this exponential relation, and we found a fractional exponential. It's not an integer. Is a characteristic of spin glass behavior. And the n here we got is about 0.4506, and the time constant is estimated to be 1668 seconds. Well, the same thing happened for the field cool situation. So this result indicates that when we do this type of susceptibility measurement, people have to be very careful because the time dependent of the signal. So you really need to take some time until it reaches to the equilibrium. Okay, and this also indicates there's a spin glass behavior in this material. So we look at in more detail, and we found a very interesting switching phenomenon. That is shown in this graph. We look at the magnetization. For instance, in here, the first one we cool in 30 Gauss, and start from this temperature. Then you can see it first become a diamagnetic. Well, let me use the next graph, probably much clearer, which expands scale. You can see the dot point, they go switching to the paramagnetic state. Okay. And the same thing for the 60 Gauss, 70 Gauss. You can see the jump from diamagnetic to paramagnetic. And we plot that, the transition temperature as function of the field. You can see it's reached when you have the field above about 90 Gauss, you expect this transition disappear. That's what happened in here. We look at in 100 Gauss and 200 Gauss. Okay. Here, the first curve at the bottom is the pure yttrium-bearing copper oxide, and which we look at the X-ray structure. It shows a single phase material with a transition around 96 degrees and transition with about 3 degrees. Okay. And when we start to add the strontium, the room temperature resistivity starts to go up very rapidly. And you can see, and the transition temperature starts to shift to lower temperature. Okay, this is the curve for 0.44 strontium and then 1.2 strontium. Okay, here I showed the whole spectrum we have. Here's what we see. Okay, from the pure yttrium bearing, then we have a 0.4 strontium goes up, TC goes down, and this goes up again. Then when we reach it to about 1.4, actually it's 1.3, then you start to see a very interesting anomaly in the resistance behavior. When we cool it down, it first behaves like a semiconductor. Okay? And then it goes through a peak at about 200 degrees Kelvin, and then start to drop. And the the decrease of resistance is essentially linear, like the other pure or high barium concentration sample. And we look at that, we show there's no hysteresis at all, okay, for this banding. And we look in more detail near the critical concentration. Here we plot the 1.4, 1.45, and 1.5. You can see that when you go beyond 1.5, essentially semiconducting. There's no longer any superconducting superconductivity in this material, and the activation energy was very high. I haven't calculated that value. But another interesting observation is here, the inflection point, or the peak resistance temperature is shift down, before it goes to a purely semiconducting phase.